Hello, my name is Kumar. Today we are going to talk about data as of platform, which allows you to travel in time through data and metadata. But today our focus is on metadata. And in this particular video, I'm going to talk about the theory, the algorithm, functionality, and the various data structures, how they work. And the next video, I'll walk you through the demo. And then in another video, I will walk you through the implementation details. Okay. So yeah, we want to build a SaaS system that never forgets. That's a goal. So ultimately, the goal is as you look at data and metadata, what's happening in real life. As days go by, data constantly changes. Um, every day, like let's say this is in day sometime last month, and then the next day, because of daily script and nightly script, the data gets changing. Every day the data changes. Similarly, business events happen, and then metadata changes. The dimensional, this is the collection of dimension, which I call it as a metadata. They all change, like product hierarchy changes, bill of material changes, sales hierarchy changes, and so on. Um, so most of the enterprise systems, they maintain the latest data with the latest collection of dimensions and hierarchy. So they operate here. Assume K is the latest time. But if you want to do a, let's say, comparison quarter over quarter, they may use some kind of a clumsy IT backup to take the snapshot as of last quarter and then use only the latest hierarchy. They will not be able to give you a perspective of what the data look like as you saw as of that time. Okay, so they will never be able to do this. Okay, so what we want to build is as time goes by, as I say, data and metadata changes, it's an ability to provide any combination, this with this, this with this with this, and so on. So for whether it's a calculation, aggregation, allocation, or any type of analytical operation on this data against any hierarchy at any point in time. Okay, so basically view data for snapshot ti using metadata for snapshot tj for any I comma j. So that's a system we are trying to build. But today the focus is on how do I maintain these various metadata snapshots over a period of time. The next one we'll look at how we maintain the data snapshots over a period of time because the strategy is different. Okay, data is humongous, metadata is manageable. Okay, so also another thing is anyone who's been implementing nowadays probably have a solution. If they do, it's probably a one-off that works only for their customer, or they paid a lot of money to consultant to build a proprietary solution. Most of them end up doing a copy. Okay, once you have a copy, it takes up n square space. Then you won't be able to keep everything in memory, because, or you may not be able to keep too many of these. Okay, our algorithm maintains order of n plus k, which is linear in space. So this allows us to keep all versions for the entire history in memory, and that allows us to efficiently switch versions dynamically. So this is based on a paper by Tarzan and Slater from a bunch of guys from CMU that came up in, I think, in early 80s. I used that a lot of the ideas in my PhD thesis, so I'm pretty familiar with what that paper does. So that's the crux behind this idea. So also, like if you just store a smaller amount of if you store this, then you will be able to do a lot of diffs and changes and all of that. If you maintain a complete copy with a lot of redundant data, that prohibits you in doing some efficient operations. Okay. So what's the architecture? So how we want to deploy it? We want to coexist with the existing enterprise vendors like Workday, Oracle, SAP, um, Anaplan, OneStream, and any JDBC export-enabled application. So what we are building is we're building a Java Spring Boot middleware, um, and that allows for you will see in the implementation there is quite a lot of REST API, and I have my own database for storing a lot of the user details, and then all the metadata versioning stored in this relational database. But data is stored in a data lake, and we use Apache Iceberg format, and then Apache Spark SQL with the NetC catalog to access the data. So that we will go through it at a different time. So what I'm hoping is on a daily basis or a hourly basis, you can export the data, and each time you can create a version. Those versions would be efficiently maintained, and then you'll be able to access it through the REST API, and then you can either use our client to view all the hierarchy and data at any point in time. Because this is being built now, everything is AI and LLM focused. There is a lot of agents, almost more than 10 plus agents in our UI. I also have an MCP server that allows you to access it through MCP clients like Claude and ChatGPT and so on. So eventually, I want to build plugin to Excel, Google Sheet, and also BI connector. That is all coming using SQL and MDX interface. Right now, using the REST API, you can either you can yeah, and the UI is built in the Next.js and React technology. It uses the REST API to render all the data. Okay, so I'll demo all that. Okay. But we also prefer if the vendor wants to take, it's all implemented using microservices and a collection of Docker containers. Those can be deployed within a vendor cloud, and they can use it as an internal deployment and access the REST API. So instead of exporting to our SaaS, they can locally call the REST API and maintain various snapshots. And then that becomes their UI, and we should be able to even ship a reusable React components that they can plug in their own software, or they can use again MCP clients to access that. Or but the key thing is they don't necessarily have to use our SaaS deployment. The both are possible. So the metadata snapshots over time. So the UI would look like, so basically you will be able to see in our UI, you're looking at a snapshot. You can almost like flipping through the music album. You should be able to pick any dimension, pick any snapshot or a version, and you can look at it. We generate an LLM commentary, all the insights and the details, and then you can flip to the next one and so on. You should be able to even compare the two of them. You can pick TI and TJ, and you'll be able to compare the two of them. And then we should be able to do some variance between what has happened to this dimension over that period of time. All that is possible. And this all happens because of the linear space, and the data structure is pretty efficient to, the APIs are pretty nice to get all these details pretty quickly. Okay. Data snapshot we'll skip over for now. So what are the master data? So this is also, I'm not only building a time travel metadata, but also I'm building a master data management or a metadata management. So I've seen a number of pain points over the last 20 years, and I'm trying to solve all of them at the same time. So this will become the ultimate the metadata management for any enterprise software. They can even replace what they have with this, and being able to use these dimensional and hierarchical concepts using this software. So I'll walk through the taxonomy and the different concepts that are supported. So everything is versioned, right? Any change is version. So it is called version dimension. Also, you can call it a slowly changing, because as I described in my article, changes to the metadata does not happen at like a transactional frequency. It's not happens every millisecond. Every change is an important business event. You don't hire an employee just like that every millisecond. We're adding an employee or moving an employee from one manager to another, adding a new product, adding a new cost center, or changing the bill of materials, adding a new sales territory, and all of that or happen slowly. That's why it's called slowly changing dimension. Okay, and we want to version all of them. Okay, that so every change is version. So the taxonomy is you have multiple dimensions. Each dimension can contain everything is version. There is no exception to it. Whether it's a time or metric, everything. And every dimension can contain lots of hierarchies. So we support alternate hierarchies on the members of the members uh, belong to the dimension. They are shared by all the hierarchies of the dimension, but we don't clone the member if you introduce if you use the same member in two hierarchies. Okay, member is there's only one copy of it in the entire dimension. The edges, of course, are between two members. The edges changes between hierarchies, right? So edges is nothing but in any hierarchy, you basically define how the members are related in that hierarchy, right? Parent, child, grandchild, sibling, and whatnot. There's also another notion of a property. We have a notion of a property which is supports all kinds of types like string, date, number, even image, and you can associate it with a member, an edge, hierarchy, dimension, and all of that. This allows you to, like, let's say if an employee profile, they change their image multiple times. You can go back and look at it how their profile changes. If somebody changes their last name multiple times, you can change it. If they change, so any property is also versioned. So you can go back in time and look at it. Okay. So hierarchies are directed acyclic graph and tree. What that means is normally in most of this is another pain point that I was talking about. This caused so many issues in a lot of examples in bill of materials in particular. Yeah, finished good uses bunch of parts. A part can belong to multiple finished goods, so it has got multiple parents. Similarly, somebody may report to two different cost center at two different working hours or working ratio. And a January may belong to multiple calendar hierarchy, fiscal hierarchy as well as calendar hierarchy and so on. All of them are naturally modeled using the DAG, and I'll go through those examples. Okay, so the hierarchy support multiple parents, and also there is a in because I said a bicycle may contain two tires, so there's an edge weight which is modeled using the edge property. Okay, so version is an important concept, and that drives everything. A version has got name, version number, unique ID, creation time, and all of that. Um, and this is tagged with every change. Okay, so let me skip all of these and I will walk you through that, and then I will come back to this concept, because once you see it, then and the demo and all of that, finally we can walk through that. There are a lot of, as you can see, so these are all the various pain points that I have, and all of them are supported using this, not only time travel metadata management, but really the ultimate metadata management that I want to create based on all the pain points I've seen over the years. Okay. Um, Let me now walk you through different examples. I'm going to take two or three dimensionals, and then I'll show you how the theory or the algorithm works. So bill of material dimension as it evolves over time. Okay. Let's assume there is a finished good which is created in version 1. So because I support multiple roots, the system automatically creates what is called a virtual root. So every dimension when it is created, there is a virtual root available. So that doesn't belong to the dimension. I mean, it is there. Okay. So this is in version 1. Okay. Now, so that is tagged as version 1. That's how the data structure works. When you in version 2, let's say you add three children, subassembly 1, 2, 3 to finish good 1. So now we don't make it. This is where the n square is avoided. So we don't clone the hierarchy and then make changes to it. So we modify the existing hierarchy in place. So basically FG1 is not cloned, and then tag them with version number 2 or 2. Okay, so this is allows us to travel back in time and query who are the children of FG1 in version 1. It will say there are no children. If we say version 2, it will be able to find that. Okay. Now, similarly, I add to subassembly, I have a bunch of parts in version 3. Okay. Now let's go to in version 4, I add another finished good. So now in virtual root, if you say who are the roots, in version 4 there are 2, version 3 there is only 1. Okay. There are all kinds of queries supported: roots, children, siblings, parents, ancestor, descendants, and all of that. And every query is versioned. So all of them are supported through the API. Okay. So now this is where the directed acyclic graph comes in. Now let's say I added subassembly 3, 4, 5, and to subassembly 2 in version 5, I'm adding FG2 as a parent. You can see now SA2 has got 2 parents. Okay. So this is not modern in any of the modern systems, or someone has to write some clumsy or a custom proprietary tool. We want to support it to all customers out of the box in a very easy way, like the way you model in any software, any enterprise software. You modeling an hierarchy is like well supported. Like we want to model this in a very easy way, as well as the time travel capability. So this is why hierarchy is a directed acyclic and not a tree. So there is a beauty of this. Okay. So once you model multiple parents, there is no difference between, so you have a root and a leaf mainly because it is growing in one direction. But when you have multiple roots and multiple leaves, and you can even today, you can even have a more roots than leaves. So there is no difference between an aggregation and an allocation operation. So once a node has got multiple parents and multiple children, aggregation and allocation mathematically look the same. WI comes from edge weight. So basically, whether you are multiplying all the descendants with the weight and aggregating to a parent, or take the value in the multiple parents, multiplying by the weight and aggregating to the or allocating to the children, is the same. In supply chain and the bill of material use case, what will happen is you will have a dependent demand goes from finished good, gets blown up by the scale factor into its subassembly, and then it propagates recursively down the thing to compute to make this finished good how many parts I need. Similarly, if you want to compute what is the total cost of a finished good, you take the cost of a part and then multiply them by the scale factor, aggregate it to the subassembly. There may be a assembly cost, and you add that and then multiply it by that, and you keep aggregating all of them back to the root. So you can see mathematically it's the same. So this is what is fundamentally supported in our platform. We don't differentiate between going top to bottom or bottom to top. Like that mathematical symmetry is beautiful and makes it easy for a lot of good application. Okay. So now keep going. Like in the 6th version, if you do this, so there is no difference between that. So this is well supported. Okay. Now you can make more complication and all that. Now let's add. Let's say now you are adding the edge property 3.5. You can see like all of these have an edge. Okay. Now this is what I meant by when you want to finish good 10 of them, you have to multiply 3.5, and you want the 35 of subassembly 1. So that's what it means. That's how the supply chain world works. Similarly, if the cost is something, now you multiply that by 1.7 to figure out the cost of subassembly. That's how the math works. It's not a simple aggregation. And this can change. Like for example, iPhone design has changed over the years. The number of the bill of materials of iPhone over the years, like has used different amount of disk drives and whatnot. Um, so edge weights example of bill of material, like I talked about. In time dimension, for example, if you take a week does not end in a nice monthly boundary. If there is a week that spans, let's say, January and February, if there is a weekly sale, how do you compute the January sale and a weekly and a February sale? You need to give it, if 3 days fit in January, 4 days fit in February, you need to do a weighted aggregation. And I've seen in my own example working in the other software, this was extremely difficult, and we got this requirement from a bunch of customers. We had to write a lot of custom code to deal with it. So this is built out of the box from here, and you will see an example in the slides down. Okay. Similarly, in consolidation use cases, the entities they all report to different cost centers, and there is a minority interest. There are various ratios, and you need to apply that. Similarly, employee, this is not easily modeled. If an employee working for one cost center 70% of the time, 30% in another cost center, if you want to do an accurate budget aggregation, you should use that. And that's not possible today. And unless you do a lot of custom SQL or something like that. Okay. And because of the mathematical symmetry I talked about, this aggregation and weighted aggregation, both top to bottom, bottom to top, are naturally supported. Apart from the time travel, this is what I meant by this is like I felt like I built the best metadata master data management solution out there. Okay. Now you can see the property change. Let's say in the new evolution of finished good 1, they want to use 4.5. And this is also version, and remember, you can go back in time and look at how these things are changed. Similarly, an employee may suddenly the ratio of reporting to various costs can change and so on. Okay. Now let's say you delete this. Even the deletion, the data structure, you can see changes are very complicated, but it is internally maintained. Suddenly what happens is in the 10th version, subassembly 2 is deleted. It still remembers subassembly 2 belong to FG1 in version 2, but I maintain enough edges and once this is deleted, all of these directly report to the grandparent. And that information is stored. Now, if you query who are the children of FG1 in version 10, the algorithm will traverse that appropriate label and then find out P4 and all of that. This is what makes it linear space, and then being able to easily identify the diffs and being able to nicely generate an LLM commentary and all of that. If you store the entire thing, you don't know in a very succinct way what changes have happened. Okay. Um, so this is how it looks without all the complicated edges. But now I'm let's say I have an alternate hierarchy called BOM alternate hierarchy. It's the same finished good, but they have a different set of edges. I couldn't draw both of them at the same time because the picture is too complicated. But here it is growing pretty fast. Okay. Within 3 versions, all of these are built out. Now P3 will have edges to SA1 of certain type, which all of them are version in this hierarchy. Similarly, it may have a collection of edges to the various subassemblies in the previous hierarchy that I showed you. Okay, and all of them are all version. Okay, all these complexities maintained, and then you can query through any hierarchy. Edges belong to an hierarchy, and you will be able to figure out what the relationships are in that. And multiple hierarchies, again, it's linear space. Okay. Now let's go to time dimension. So this is a beautiful concept. Let's say you have all these months. So I'm drawing Oracle, where I worked. Oracle fiscal calendar started in June. Okay. If you have June sales, okay, June sales is June sales, but you can report it in different way. If you want to say what was it contributes to fiscal Q1 of 2025, but calendar Q2 of 2024, the same thing. So this is possible out of the box using the alternate hierarchy. Okay. Now the next one is, let's say week 1, for example, in week 1 of 2025, if you look at 3 days belong to December, 4 days belong to January. If you have weekly sales, how do you aggregate that? We had a situation where one company acquired another company. The first company had a monthly calendar. The second company had a weekly calendar. So we needed to somehow transport the data from one to another. That wasn't easily possible without writing a lot of custom code. So this allows you to naturally model. You can put any ratio you want. You can include weekends, only weekdays, or if you want to give preference to this, all that is possible. So for example, this completely belongs to January, so the ratio is 1. Okay. So this edge weight is a beautiful concept that opens up a lot of application, and you don't have to go through a lot of hassle to model that. It reduces significant consulting dollars. Okay. Now let's go into employee dimension. All of these I will demo in my when I create the demo. In the first version, let's say John is the employee, and then John gets 3 children. Nothing interesting, all of these. Then all these some more employees, and then some more, and some more, some more, and so on. So you built out this in seventh version. Now I have support a lot of operations like reorg, like moving with the your reportees, without your reportees, become a root, delete, all of that are possible. I will show you how that. So next one is, suppose Walter stopped reporting to Steven and he starts reporting to Ashley. So now this relationship is ended as of he only got added in version 7. He stopped reporting at 7. Now this is how the data structure is internally constructed. Now Ashley starts managing Walter from version 8. So Ashley's children in version 5, 6, 7 is only these two, but in 8 it's Amanda, Justin, and Walter. Okay. And even the descendants will start to have these things. So I have some nice LLM demos where you can query for this. Hey, who are the children of Ashley? Who are the descendants of Ashley? And all of that. You can put a time, and then I look up a version by time and all of that. You'll be able to see those. Okay. So this is without the complicated edges. I have two display, one with the complicated edges, one without them. Now in, let's say, ninth version, what happens is Olivia stops reporting to Stephen and moves under John. Okay. But without his children, without our children. So Charlotte, and so naturally they belong to our manager who's Stephen. So that edge is there. So we say move with children, move without children, and then it belongs to John. Okay. So without that complicated, this is how it looks. Olivia no longer has any children. She reports to John, and then these two report to Steve. Okay. This is similarly, suddenly Amanda becomes the root. Okay. And that is also supported. It's and then all the adjustments happen. And without that, this is how it looks. Okay. Dexter, who was a child of Amanda, reports to her. And 11th version, like same thing. And these are all similar so this is a nice one. So Amber now decided to leave the company. She will come back after some time. There's a very popular terminology used in the HR world called tours of duty. Like for example, a lot of people have Oracle is like a mothership. People have come and joined Oracle multiple times. The Oracle does this something unique, maybe other companies do. If you rejoin again, you get the same employee number. They call it a multiple tours of duty. Okay. So I model that naturally. Okay. When a member is created, I create a tour of duty property because there's a process, it's a system property with that version. And when it gets deleted, I mark that tour of duty ended in this version. So you'll be able to, this is what I meant by LinkedIn profile. You can nicely generate an automatic LinkedIn profile. Hey, what has happened? So you joined this and this version, and then he started reporting this person, and then he changed there, and then he left the company, rejoined again. So this is not just for employee, for any dimension. Okay, so this gets deleted and it gets marked, and so how do you know it's same Amber? Like you have to use some unique ID. Like I think companies probably use social security number. So we need to have you need to use the same unique name when you that unique name is is supplied by the customer. Okay. So this is basically without that complicated edges. So now it keeps going. At some point, that's more deletion example. Okay. So there's nothing interesting. So for example, Amber comes back. This is the multiple tools of beauty. So she was reporting to Olivia in 78. Stephen is the parent 9 to 11. Got deleted. Now she's uh, belongs to now Gloria. Okay, that is modeled out of the box. Ashley one. The only reason I'm modeling that is it's the duplicate member name. Okay, so unique name is Ashley one, but they share the same name called Ashley, which is pretty common. Okay, so that's what, and then let's keep going. Effective data hierarchy, right? This so far we saw slowly changing dimension. Effective data hierarchy is basically in sales planning world. Suppose this could be like hundreds of VPs in an organization who are all sales VP because they're all managing different P&L. They all want to do look. They're looking at their current officially published hierarchy before the quarter ended and the new quarter starts. They want to muck around. Okay, what if I add this new territory? What if I combine them? What if I move John to Chicago because he has a buddy there? They want to play around with it, and they want to create multiple copies of it. Not only create a copy of it, and you want to show the effect of those hierarchy on the data. Okay, this is where like the original picture, aggregating data over different hierarchies is very, very important. There's also version specific. Effective data hierarchy is also used for company reorg, whether they are laying off people or merging with a company or merging two departments. They want to play with the hierarchy and being able to look at the impact of that on the budget or any underlying data. Okay, and that is naturally possible. And many companies may have this. They probably paid lots of money to their own developers or consultant build a unique proprietary solution, and this now is a generic platform which will work for anyone. Okay, so you can model this one. Let's say you have a departmental hierarchy. You can model something like, what if you eliminate department 4 as of June 2025? Okay, or what if we combine two areas into one? Area 5 goes away, and then you can imagine this is, and then you want to study the impact of this on the data, right? Not just you're not just making changes to the metadata, but you are studying the impact of the changes on the underlying data. Okay, so this is another one. So I've seen so many places where if some consultant screwed up the nightly ETL script, and then instead of loading at a weekly level, they load it at a daily level, and then some lot of the dimension from suddenly from 100,000 blew up to 10 million because they loaded a lot. You are supposed, let's say you only want to deal with bill of material to level 7, they loaded up to level 35. What do you do? That your data is corrupted. The only way is like file a support ticket and you have to go restore it and then whatever. Because everything happens in a version, you can simply undo it. Okay. So this is the beauty of it. Let's say you are today you are from hierarchy 1 to 25, and somehow 15 to I'm kind of exaggerating, 15 to 25 is corrupted. You can rewind to that version, call it a new hierarchy, start using that. And when you rewind from version 1 to 14, again it's not n square. I don't copy that at all. I have a notion of effective data hierarchy as a source hierarchy because it's a read only for this, because anything in the past is read only. I don't touch it. So I have a reference. I make pointer manipulation to go read that. Even so, when you go and if I go do a select count star in the database, the edges will not grow. It's just a metadata reference saying, look, I need to start using in this source hierarchy from version 1 to 14. Any new changes, of course, will happen here. Okay. Similarly, you can rewind or you can selectively rewind is you take the entire thing. Undo is okay from 1 to 25. Yeah, I like everything, but I only want to undo 12 and 13, 20 and 22. This is little, it's like a kind of an hammer looking for a nail. I came up with this cool idea, but I don't know. Maybe this is almost like a software bug. So even not just a consultant bug, let's say your yesterday's service pack had a bug and it screwed up, and now you don't need to worry about all the corruption. You can, or even if you somebody nobody discovered, and then this one had a bug, you can nicely unwind that. So it helps in consultant issues, software bug, being able to play around with sales managers can explore, and then a new design you can explore. So the possibilities are endless. Okay, so here you can selectively undo, and here what I'm here it's undo is you're kind of a picking and choosing. There are three terminologies: rewind, which is completely rewinding; undo is a kind of lockout kind of a thing. You can rewind and then selectively reapply. You're rewinding to 17, and then I'm picking, oh, I want to apply 20, 23, 25. Some are changes I didn't like. Okay, so I'll be able to demo all of these. Okay. Then the other one is metadata translation, right? So Space had this beautiful idea called alias table, right? Every member had got. So when I was a VP of engineering, when I started, it was only at 20. I expanded it to 65 or something. So every member can have. So consultants use that to do a lot of amazing things. So one of the cool thing you could do is the language translations. If your company has multiple offices, you can store translations of the metadata in all those languages in the alias table. Okay. So because you can, I pointed out, I have property. Property is a bag of things, and there is no limit on number of properties you can have. Okay. So I may at some point impose a limit. Because of that bag, I'm going to, similar to tours of duty, I'm going to define a system defined property called translation, and it will have a simply uptake translation file. I'll be able to simply take out of the box various language translation for the metadata. So I can support it in various formats, CSV, JDBC, or whatever, and you'll be able to see your metadata in multiple languages. So all these you will be able to see in the demo. So that is the theory, and so in the next demo, I'll walk you through the software. Okay. So with this, let me end this.